girls, we start lecture section 6.1 in real analysis. Okay, and try see what happened. Okay, today we talk about differential. First, I give you definition. We have some interval I, real numbers, and f, some function from I to R. And let's see some number from our interval. Function f we call differentiable in point C if for any positive epsilon exists positive delta, depend for our epsilon, for any x from such will be better. Such distance between x and c less than delta, fx minus fc divided by x minus c, absolute value, minus some number L less than epsilon. This number L, it will be derivative of your function phi in point S. What does it mean? It means derivative function f at point C will be limit x approach to C fraction fx minus fc over x minus c. Here we have some theorem who tell us, theorem 1, if function f from I to R differentiable at C, at C, then our function is continuous at C. Then function f is continuous function at C. Try prove this fact. Proving. If derivatives exist, and first, for any x not equal c, we can rewrite f x minus fc. I'm divide and multiplied for x minus c. We know it's oops, just a moment. It's true for any x who is not equal c. This means any non-zero denominator. Because we have this kind of equation, take it limit both sides, limit x approach to c, fx minus fc will be limit this fraction Because limit from product equal product limit, we can rewrite equal limit fx minus fc x minus c x approach to c times limit. Sorry, I'm clear a little bit. I need more space. It sometimes takes more time than I think. Okay. Okay. Time limit x minus c x approach to c. Because our function is differentiable, this means limit our fraction equal some number L multiplied by 0, which is equal 0. This means we have limit function fx if x approach to c equal f value function f in point C. We prove our theorem. How you remember in calculus class, opposite is not working. This means if your function is continuous, it's not mean derivative your function for this point exists. How you remember, I think, example, function fx who is equal absolute value x. This function is continuous for all real number, but for x equal 0, derivative function not exist. I think we easily can prove this fact because absolute value x is equal x if x positive, 0 if x equals 0, and negative x if x less than 0. If you try found derivative, this means, let's go, we have limit absolute value x minus absolute value 0 divided by x minus 0, whereas x approach to 0. It will be limit absolute value x divided by x if x approach to 0. But this limit is equal 1 if x positive and negative 1 if x negative. This means this limit is not exist. It depends what way you go to try be close to x, right or left. Because you have two different numbers, this means limit is not exist. This means the function doesn't have derivative for point x equals 0. Now we study one more theorem. No, I think we are looking for our, just a moment. Yes, it's theorem, but it's looking for property our derivative. Let's we have two functions. Function f from I to R, function g, I or R, and point C from our interval. Sometimes it's not working, sorry. And derivative function, both of function differable, oops, for point C. Then we have alpha f, take a derivative and put point C is same like you have alpha and f prime and C for any number. For second, plus or minus g, take a derivative for point C, it will be f prime C plus or minus, depend what you have before, point C. Third one, if you have product to function and then you want to take a derivative, it will be f prime C dc plus f c d prime c. And fourth one, last one, if you have fraction, it will be minus f c, oh my god, g prime c, and divide by square of function for point C. Now we can prove, well, because proving is very similar, I prove number 3, for example. And you can prove all other if you want. Okay, clear? Let's go. We define new function p, who is product our function f and g. And I try found derivative my function p and point at point C. Limit x approach to C, it will be p x minus p c divide by x minus c. You see, I'm only write definition, nothing more. But now I need to remember what is my function p is. It's product to function f and g. This means it will be limit fx gx minus fc gc divide by x minus c. X approach to c. Here we use trick, how we use usually, if we need something proof. Not usually, but often. We add and subtract something same. Here I'm doing this one. fx. Sorry. I'm subtract fc c gx, and then I'm at same product. This means value my function f in point c multiplied by gx minus fc gc divide by x minus c, x approach to c, equal. Here we separate for two fraction and factoring, and we have limit this is my first fraction plus limit. Here I have gx minus gc over x minus c, x approach to c, times f to the c. And here we can see the c. Fraction is derivative, value derivative my function f in point c. This means f prime c times second product, and he'll be second factor, it will be g point c plus, here we have f c times g prime c. We prove number 3, and I think you can see easy. All other property of derivative we can prove use same method. Now we have one more very interesting theorem. I clear my table. This is called Theodoros. I think it's Greek mathematician. And we have interesting theorem who help us for solving some interesting problems. This theorem tells us let's say have function f from some f from some interval I to r, and point c from, oops, it's changed my color, sorry, c and I. Then function f is differentiable at c if and only if exist function phi continue point c such as differ between fx and fc. We can rewrite like product our function phi x times x minus c for x from our interval I. In this situation, derivative, value derivative your function f will be value derivative your function phi in the c. Okay. How we prove this fact? Prove one way, because it only and only, this means we prove two-way. Let's go this way. This means function f is differentiable at c. Let's build function phi x. Function phi x will be function fx minus fc over x minus c if x is not equal c and equal f prime c if x equal c. Now we need proof this function is continuous. Okay. How we remember definition derivative limit fx minus fc over x minus c. If x approach to c, it's exactly equal f prime c. But f prime c equal phi c. And what we have? We have limit our function phi x. If x approach to c, it's exactly equal phi to the c. This means function phi is continuous function and value at point c is equal value derivative function f at point c. Great. Proof second part our theorem. Sorry. Proof this way. Let's go. Our function phi x is fx minus fc over x minus c. Because function phi is continuous, this means limit phi x for x approach to c equal value phi c. Use this fact, we only rewrite definition x approach to c f x minus fc x minus c. Use definition derivative is will be derivative function f at c, but at the same time equal phi at c. And we're proving our theorem. This theorem we can use for proving our chain rule. I not prove in the class. You can read in book, or because chain rule is some rule very useful and you study this theorem in your calculus class. But now we only remember how its theorem work. Okay, let's go theorem. If f is functions for some j interval to r and g is function from I interval to r, and you have f from j, it's from interval I. Then we have composite function gf, and for this composite we have j composite f, take a derivative at some point c. It will be j prime from f c times f prime from c. Doing some example when we can found derivative. For example, let's go, our function is hx is sine x to the power k, and our function power m. Here we have composite three function. Power function with power m, trigonometrical function sine, and power function for power k. Okay, what will be derivative here? H prime x. First we're doing derivative for power function with power m. It will be m, same base, okay, but power now it's one less, m minus 1. This situation is n and m is both of natural numbers. Multiplied by derivative, next function, this means derivative function sine, this will be cosine x to the power k. And times derivative x to the power k, it will be k x to the power k minus 1. Here we found derivative, use chain rule. Now I show you one of question, was this homework, but I think it's better if we're solving now. It will be, just a moment, it will be this kind of function. Okay. Because this time writing is not perfect. I hope next time it will be better. And I think I show you this question from homework. It's a little bit help you. Let's go, we have function f from r to r. And this function is definition, this function fx equal x squared if x is rational number, and 0 if x is irrational number. Proof, we need proof, or we need show derivative this function is 0.0 is exist. And if we can, we can proving. Okay, let's go. What we have here? We have a limit x approached 0 f x minus f from 0 divided by x minus 0. We need found this limit. Oh, first we can see value our function is 0. It will be 0 because 0 is 0 square is 0. Okay, this means here I have limit fx divided by x if x approach to 0. In our question, how I can do it, how I can counting this limit. All we remember, if we have function, we can build some sequence who is approach the same number and see what we have. Okay, here we have two sequence, for example. Let's go. Let's xn equal 1 over n. What we have here? 1 over n is approach the 0 if n approach the infinity. And here is rational number. This means here is limit f from xn over xn and approach the infinity. It will be 1 over n squared divided by 1 over n, limit n approach the infinity. Here will be limit 1 over n and approach the infinity, who is 0. This is, I give you example, but you can see for any sequence xn, whereas xn is rational numbers and xn approach the 0, limit xn squared over xn and approach the infinity, n approach the infinity. Oops. You have exactly limit xn and approach the infinity. It will be 0. This means question, what happened if we try build our sequence who is irrational number? Okay, great. But if we have I try save here. Let's go yn. It's irrational sequence with irrational numbers, and yn approach to 0. What will be this limit is this situation? Limit, oops, fyn divided by yn and approach to infinity. But here is numerical, this fraction is exact 0. This means you have limit 0 over yn. Approach to infinity, and this will be exactly 0. We prove our fact. This means it's not depend what kind of sequence you have. If your sequence approach to 0, your value, your fraction is approach to 0. We prove this limit is exist and exactly equal 0. This means value derivative for our point 0, it will be 0. Great. Okay, girls, doing your homework, please. Sorry for what happened to today's lecture. And if you have any question for homework, ask me. I try putting my lecture is faster and see what happened. Will be free, write me email and call and doing any kind of connection. Okay, good luck.